Algebra 1, Lesson 108, we are identifying and graphing exponential functions. So first we need to look at this formula. And if you remember back just a few lessons ago, we used this to show our geometric sequences, to say the value of any number in the sequence, a sub n, is equal to the first number, a sub 1, times our constant ratio to the n minus 1 power. Well, kind of like we talked about, this is actually an exponential function. We use it to show our geometric sequences, which are truly just exponential functions. So the definition is a function in the form of f of x equals a times b to the x power. This is our exponential function formula, just slightly different than our geometric sequence formula, where a and b are non-zero constants and b is a positive number not equal to 1. So we got to make sure that this value, this b value that is the base of our exponent, we need to make sure it's not 1, or else we would just be multiplying a by 1 over and over and over again. So if we were to evaluate a given exponential function, just something simple like f of x equals 5 to the x power. So if I wanted this, I could say, well, if I want x to be -3, 0, and 4, I need to plug in those values in order to get the value of the y. Okay, we have the x, we need the y. So we plug them in and we say f of -3, so x is now -3, is equal to 5 to the -3rd power. Well, we can simplify that with what we know about negative exponents to say that's 1 over 5 to the 3rd. And we simplify again to say that's 1 over 125, which means I have a point on this exponential function at -3, 1/125th. We tried again with 0, so f of 0 is equal to 5 to the 0 power. Well, anything to the 0 power is 1. So we say we have this point at 0, 1. Okay, little hint here, that's your y-intercept. Okay, it means that the a value is really important. Okay, in this one it's 1. All right, and lastly, f of 4 is equal to 5 to the 4th power. So we do 5 times 5 times 5 times 5, and we get 625. So you can see how quickly this grows. By the 4th term, okay, by x as 4, it has gotten really big very fast. All right. Evaluate for the given value, so let's try it again really quick. I'll just do 1 or 2 of these. So now we do have an a value that we can see in this next one. F of x equals 2 times 4 to the x power. So if I plug in -1, 1, and 2, I'm going to say f of -1 is equal to 2 times 4 to the -1st power. And now only the 4 has the -1st power, so I can put it as 2 over 4 to the 1st power. Okay, just moved it to the denominator, which really is 1/2. So I have a point at -1, 1/2. And then I say f of 1 is equal to 2 to the 4 to the 1st power. 4 to the 1st power is 4 times 2 is 8. So I have a point at 1, 8. And lastly, f of 2 is equal to 2 times 4 to the 2nd power. Well, 4 squared is 16 times 2 is 32. So we have a point at 2, 32. All right, and then you can try the last one on this page. I'll just do this one for us. So if I have f of -2, I'm going to have -3 to the -2nd power, which means that I have 1 over -3 squared, which is really 1/9. So I have a point at -2, 1/9. And then I try f of 0 is equal to -3 to the 0 power, which is just 1. So I have a point at 0, 1. And f of 3. That is equal to -3 to the 3rd power. Well, if I do that, I'm going to do -3 times -3 times -3, which is -27. So I have a point at 3, -27. All right, kind of a funky one there. All right. Now, Let's say we do this one here, 4 times 2 to the x power, and we plug in all of these different values. Well, when we plug in all of these different values, so if I plug in -2, I'm going to get 4 times 2 to the -2nd power, which means I have 4 over 2 squared, which is just 1. I plug in -1, okay, ends up very similar, but in this case I get 2. Plug in 0 and I get 4. You can check all of this on your own. Plug in 1 and I get 8. Plug in 2 and I get 16. Now I want to see what this pattern looks like, because supposedly it's supposed to be a geometric sequence. Well, as I increase my x by 1, okay, it looks like every time I multiply by 2. Okay, we can see this pattern. As we increase the x by 1, we need to multiply by 2, which means that this 2 in here, the base of our exponent, is that ratio that we have, just like geometric sequences. In this case, we call it b. In geometric sequences, we would call it r, but it's the same thing. It's that constant ratio. So an exponential function must increase by a constant amount for both the x and our y, f of x. So x will increase by a constant amount, while f of x will increase by a constant ratio. So as we increase x by 1, so adding 1, we actually multiply to get from y to y value. Okay? So we need to determine if these sets of ordered pairs is an actual exponential function. And the first thing I need to do is write them in order. So I like using a table to write these. It's a little bit easier to see. So it looks like -2 is my lowest x value. And if I have f of x, or you can call it y, I have -1/3. -1 is -1. And 0 is -3, and then I just have this last one of 1, -9. Now I look at all of these, and it looks like my x is increasing by 1 each time. So I can look at these and say, how did I get from point to point? Now if it's hard to see, this one's not too bad. If it's hard to see though, we can always, just like our geometric sequences, say 1 divided by -1/3. And -3 divided by -1, and -9 divided by -3. All of these come out to equal 3. We are multiplying by 3 in each of these cases, which means 3 is that constant ratio. And if you wanted to know the formula for this, well, f of x, if we have a b to the x power, well, f of x would be, a is actually always our initial value. We also call it the y-intercept, so we would have -3. Our b is always the constant ratio of 3, and we put it to the x power. And that's it. All right, let's try some other ones, finding if they are exponential functions. So once again, I'm going to write this in a table. So we have x and f of x, or y, and we start with 1, and then we go to 4, 3, 16, 4, 128. So it looks like we go up by 1s in all of our x's, so I can say, do we have a constant ratio? So 4 divided by 2, is that equal to 16 divided by 4, 128 divided by 16? And we can say no, these are not constant. All right, in the first one we get 2, the second one we get 4. We already know it's not the same. Therefore, this is not an exponential function. All right, here are 2 other ones that you can try. Put them in order from least to greatest. See if you can, if we are going up by a constant x rate. If so, we can just do the sequential terms divided by each other. Okay? Now, if we want to graph these exponential functions, just like we've done with lots of other ones, we are going to create a table of values. So just like we did on our last lesson with absolute value, we're going to take a table and then plot the points. Note that we're never going to touch the x-axis. Regardless of the different function, we're never going to touch the x-axis. So let's try this one. 5 times 2 to the x. And I'm going to plug in -2, -1, 0, 1, 2, and maybe 3. Okay, if we need it. We probably won't have enough room for it since these are exponential. So we plug in our values. We say 5 times 2 to the -2nd power. Well, if we do that, that's 5 over 2 squared, or 5 over 4. So 1 1/4, okay, 1.25. Plug in -1, it's going to be similar. We're going to have 5 over 2 though, so we get 2.5. To the 0 power, we're going to get just 5. To the first power, we're going to have 5 times 2, which is 10. And to the second power, we're going to have 5 times 4, which is 20. If you wanted to continue, we would have 5 times 8, which is 40, but we're going to run out of space with that. And then we plot them. So we say at -2, I'm at 1 1/4. Okay, so about right there. At -1, I'm at 2 1/2. At 0, I'm at my y-intercept, my a value of 5. 1, we're going to be at 10. And then we keep going up and up. When I connect my points, I realize that even if I were to get closer and closer here, I'm never going to touch that x-axis. It's an asymptote basically of this one. All right, we don't have a reflected curve or anything like that. This is our only curve as an exponential growth function. And so this is all we can have, okay? So exponential growth graph is going to look like that curve. Let's try another one. Now we have negative times 3 to the x value. Okay, so maybe we plug in once more. We try -2, -1, 0, 1, and 2. I would recommend doing 5 or 6 different points, some of them negative, some of them positive, so that you can see how the growth or decay works. So we plug in our value. We say -3 to the -2nd power. Well, that negative is still going to be up in the numerator, so a -1 over 3 to the 2nd power, which means I get a -1/9, okay? Plug in 1, or a -1, we get something similar, but 3 to the 1st power in the denominator, so I have -1/3. 0, well, the 3 to the 0 power just goes to a 1, so I get a -1. 3 to the 1st power, and then make it negative, is a -3. And then 3 to the 2nd power is 9, make it negative, and we have a -9. So we can see this one's going to look a little bit different than the one before, because this one has an initial value that is negative, which means that if I have -2, I'm going to be at 1/9, very, very close to the x-axis. And then at -1, I can't talk right now, I'm sorry. At -1, we have -1/3 right here. At 0, we're going to be at -1. 1, we're going to be at -3, and 2, we're going to be at -9. You can see how this is a decay. Once again, we can't touch the x-axis, but we go down, okay? Exponential decay. All right, and you can try this one on your own, but you can see how we're starting to see some patterns here, especially with what these different values mean. So our 6 here, that is our initial value. I know since it's a +6, we're actually going to have an initial value of 0, 6. We're going to have this point in our graph. And then we have 1/2. Okay, the 1/2 tells me, is this decay or is this growth? Well, since it's under 1, we say that it's decay. So this isn't going to be perfect, but we're going to have some type of decay rate that looks like this. All right, and I know that because my initial value is 6, and we have a b value that is under 1, which is 1/2. So let's compare some of these on our calculator. So we have 3 times 2 to the x value and -3 times 2 to the x. So I have them on my screen already. You can plug them into a calculator and see how these compare. But we have these two values, okay? And the first one, this is our growth, okay? This is our initial value being 3. So we have y equals 3 times 2 to the x value. And then our other one, this is still technically exponential growth, but we have an initial value that is negative, meaning that we get bigger and bigger in negatives, okay? Meaning we're going to be getting closer and closer to -infinity. So this one right here is -3 times 2 to the x value, since that initial value is a negative. All right, try it again with this one, and we can see the only difference here, we have the same initial value, but the growth rate is different. Okay, here we have a true growth rate of 2, here we have a decay rate of 1/2, which means that this first curve here, okay, curving down like this, that is a decay. So we have y equals 3 times 1/2 x. And then this one, okay, it's actually growing as we go to the right. As x values increase, we are growing, getting closer to infinity. So we have y equals 3 times 2 to the x value. Okay. All right, and last one, you can try this on your calculators again, but you can see how the initial values are different, growth rates are the same, so we're just going to have it starting in a different point, okay? The lower one here, closer to the x-axis, that starts at 1/2, y equals 1/2 times 2 to the x, and the next one, y equals 2 times 2 to the x. Just means that we start at a different place, and it really does matter because you can see that it's quite the difference between how fast they can grow with where we start. All right, and last question here, and then we'll finish up this video. So the exponential function y equals 12.28 times 1.00216, which really means that we have 0.216% growth, models the approximate population of Pennsylvania from 2000 to 2006, where x is the number of years after 2000 and y represents millions of people. Use a graphing calculator to find the approximate population in 2005, meaning our x value is going to be 5. Assuming the model doesn't change, when will the population reach 13 million, 15 million? And we won't be able to do this algebraically. We'll be able to look at a table of values and do this. But later on in your math career, you will be able to solve these exponential functions using lots of different higher math like logarithms. Okay? Now, if we use our calculator, we're going to go to our y equals, and we need to put in our function. We've got to remember our function. So 12.28, all right, 12.28 times 1.00216. Sorry about that. Pulled something else up. 216, all of that to the x power. Okay, so you can use that caret and put it to the x power, which means when we graph this, I'm going to do zoom 6. And actually, we won't be able to see it. So let's say we're going to do our window. We want our x max to be -10, 10, that will be fine. But let's make our x max quite a bit bigger. Let's say we want it to 16. Okay, so that when we graph this, all right, it's a teensy tiny little growth rate, so I'm going to change my window again. Let's make sure that I did this right. All right, and let's do our window from -2, and let's do it to 30. Okay, the reason being I want to see some amount of growth here. And it's super slight, but we do see that it's starting to curve up. That's because it has such a low growth rate, 0.216%, that we can barely see it growing over those years. We can still see it's growing, but since we're talking about millions of people, this growth, although it looks tiny, is some amount of people. Now we can also look at a table of this, okay, so that we can see in that 5th year, okay, so we care about 5th year, we have 12.413 million people in Pennsylvania. Okay, so we could have also put that in, just plugged it into our calculator. We could have said in our calculator page 12.28 times 1.00216 and done that to the 5th power. When we do that, we see that we get this 12.413 million people. Now the other question was, when are we going to hit 13 million and 15 million? So let's go back to our table and see what happens. So when do we get 13 million? Well, we're going all the way down here, and it looks like we hit 13 million right at 27 years after year 2000, which means in year 2027, we will hit 13 million people. We're going to keep going. It's going to take a little while. And the other question was, when are we going to hit 15 million? So here's 14 million, and then here is 15 million. So in the year 2093, we could potentially hit 15 million people in Pennsylvania. Okay, so exponential function, very, very small growth with this one, but we do see that it does grow. And since we're talking about millions of people, that is a decently significant amount. Okay, so I hope this video is helpful for your homework and for studying.